Okay, so let me begin. So we were discussing about a DDG, that is data dependency graph, and how we'll be drawing this data dependency graph. So one question will be based on a DDG, data dependency graph, and you have to know the difference between CFG and DDG, that is data dependency graph or direct data dependency graph. The notes how we are representing it is same as that of control flow graph, only there is a difference between edges. Edges should be labeled via variable name and edges will represent definition use pairs. Okay. And we had taken up one example, that is Euclid's algorithm for computation of GCD, and we have represented it via DDG, data dependency graph. See, if you observe the diagram over here, graph over here, the edges that are arising from each of the block are dotted. They are not solid lines. They are dotted lines, and each edge should be labeled with the name of the variable. Okay, and whichever variable is being used, okay, that should be given as a, that name should be used as a label for the next block. Okay. Arrows that you are marking are dotted over here. So the lines which you are using, they are dotted. They are not solid lines. Okay. After that, okay, what we are going to study is about control dependency. What is that control dependency? What is the difference between data dependency and control dependency? Okay. Data dependency basically deals with where the values are coming from. We are more interested in analyzing the source of the value from where we are extracting the values from which variable. Okay. That can be shown with the help of data dependency graph, DDG. What is control dependency? Okay. Control dependency, it is again a graphical representation. It will tell you about the statements which will control the execution of the next statement. Okay, that is, it tells you about which statement is going to control whether a particular statement, the current statement, that will get executed or not. That will be, that picture, particular picture will be given by control dependency graph. And how can I draw the control dependency graph? We have already drawn it, CFG. Okay, so the nodes are same as that of control flow graph, but what is the difference between the previous and this is that again with the edges. Okay, edges, as you can see over here, this is what I call it as a control dependency graph, CDG. Okay, you have something called control flow graph, direct dependency graph, and control dependency graph. How you are representing the edges? Edges are unlabeled over here and they are solid lines unlike the previous one. Okay, and there is an arrow from entry to the exit points. Okay, and it will basically gives you the overview about the execution, whether a particular block which is under consideration, does it going to decide the execution of next block. That will be analyzed using control dependency graph. And they have taken the same example, that is computation of GCD, by using Euclid's algorithm, and they have drawn control dependency graph. Here you have basically how many blocks are there? A, B, C, D, E, F, same diagram, but only there is a difference between the edges. Here they are solid lines without any labels. This is what I call it as a control dependency graph. Okay. After that, we are going to just look into dominators. Okay. Dominators with the help of this control dependency graph. What do you mean by dominators? In dominators, again have two categories: predominators and post dominators. Okay. Predominators, if I consider a rooted directed graph, okay, please have focus on these words. Rooted means I'm going to have a graph which is a directed, means it is going to have a specific arrows from top to bottom or from bottom to top if there is any traversal backwards. Okay, so I'm going to have a directed graph which is having a single root. Okay, what does this predominators? Okay, predominators. Suppose if I have a node M and node N, I will say node M dominates node N if every path from the root to node N, which is under consideration, the arrow from the root, the paths that are existing or that are arising from the root to the node under consideration, that is node N, they have to pass through node M. Then I can say node M will dominate node N, because if I have to transmit the data, then I have to pass through node M. Okay, that is how node M dominates node N. Okay. When I can say node M dominates node N, if there is a path that if there are n number of paths from root to node N, and all the paths they are passing through node M to reach to node N. In that case, I can say node M dominates node N. Okay. So in this case, node M becomes dominator. That is predominator, because node M is present before node N. That's why it is predominator. Okay, and you can also consider that a particular node is going to have many dominators, but except for the root, okay, there is a unique immediate dominator for a particular node under study, which is closest to n on any path from the root node, and which in turn dominated by all other dominators of n. What do you mean by this? Suppose I have two nodes under consideration, node m and node n, and I am interested in node n. Okay, for node n, it can have many dominators. First and foremost, you have to focus on the word dominator. What do you mean by dominator? If the path from root to node n, which is under study, have to pass through certain node, then that node becomes dominator for a node which is under study. So it's not that a particular node is going to have a single dominator. It can have n number of dominators except a root node. Okay, which one I call it as immediate dominator. Okay, the node which is closest to any path from the root to a node which is under study, and which in turn dominated by other dominators of the node which is under study. Okay, that node becomes immediate dominator. We'll look into the example in order to know about these terminologies. Okay, after that, what do you mean by post dominator? It is exactly the opposite of that. Pre means before. If the particular node is present before the node which is under study. Okay, if a node is deciding the execution of a particular node, okay, if the path from a node to the node which is under study, okay, it has to pass through a particular node which is present after the node under study, then it becomes a post dominator. Okay, you just check out for these two things by considering the example over here. Okay, we have taken up a simple example over here. The nodes are represented over here: A, B, C, D, E, F, G. Okay, see, this is the root node. It is going to predominate all nodes. Why predominate? Because A is present before all these nodes. That's why I call it as A is a node which is going to predominate all nodes, and which is the last node which is present at the end of this graph, that is G. G is going to post dominate all the nodes. That is, you have to focus upon this. You have to focus upon predominate and post dominate. Okay, that is about predominator. A is going to be a predominator for all the nodes, and G is going to be the post dominator for all the nodes. If you consider F, okay, and G, you have something called E over here. Okay, for E, if you consider the node E, which all are the nodes that are going to dominate E are F and G. F and G will become post dominators for the node E. And G is the immediate post dominator of B. See, there is one simple confusion that you may get. Okay, G is the immediate post dominator. G is the immediate post dominator for the node B. Why it is so? Why I am not considering C or E? We have already studied about the definition of immediate post dominator. As we have already seen, if there is a path from a particular node, that is B to G, okay, B can have several post dominators like C and D, G. All are post dominators, but G is going to be the immediate post dominator because it is being decided, its execution is being decided by its successors C and D. That's why G is considered as immediate post dominator. Okay, but C is not a post dominating B because the control or execution of B is wholly and solely controlled by the node G. Okay, if you look into the definition of immediate dominators, okay, look out over here. Okay, a node will typically have many dominators, but except for the root, there is going to exist a unique immediate dominator for any node n, which is closest to n on any path from the root and which in turn dominated by all other dominators of n. In this case, okay, this is going to be the immediate post dominator for the node B. For the node B, that is G is going to be the immediate post dominator for B because from the root, okay, G is going to exist from B to G. There are various dominators, that is C and D. Post dominators are C and D also. But C and D will not become immediate post dominators. Instead, G will become because G is again controlled by the successors of block B, that is C and D. That's why G is considered as immediate post dominator of B. Okay, then what about B? Okay, B is immediate predominator for G, not post. Please focus on the terms pre and post. Okay, it is G is going to be the immediate post dominator, whereas B is going to be the immediate predominator of G. You cannot say F is the predominate G because as per the definition of immediate post and predominator, G and B are satisfying those conditions. That's why I have to consider G as immediate post dominator for the node B, whereas B is going to be the immediate predominator for a node G. These are the things you have to know about dominators, predominator and post dominators. After that, I have something called the post dominators. What is the exact definition with respect to control dependency graph CDG? Okay, suppose I have to consider a node called N, which is reached on some nodes, but not all execution paths. If there are n number of paths from a root to reach n, but via certain paths, execution paths, I can reach the node n, but not considering all the execution path. Then there has to exist some node C with the following property. What are those properties? C has to have at least two successors in the control flow graph. Okay, and C is not post dominated by n. That means n is going to be present before the node C, and there is a successor of C in the control flow graph that will be post dominated by n. That is post dominated by n. This is the definition that I can write by considering control dependency graph. These three properties should be satisfied by any node C. Okay. N is the node under consideration. N is node under consideration. Okay. There must be a node with the name C Having these properties, C is going to have at least two successors in the control flow graph, and C is not post dominated by N, but the successor of C can be post dominated by N. Okay, when these conditions are met, these three conditions are met, we say that node N is control dependent on node C. In other words, the execution of node N is controlled by node C. Whatever we have studied earlier, we are explaining with CFG, control flow graph. Okay. In other words, what I can say is the C was the last decision that controls whether N should be executed or not. N should be executed or not. So, this is how I can explain the control dependency between two nodes. Okay. Suppose we have considered node N in CFG, and I'm also considering one more node called C. I can say that C controls the execution of N whenever it meets three conditions. First and foremost, C should have two successors in the control flow graph. At least minimum number of successors for C should be 2 in the control flow graph, and C should not be post dominated by N. Here the word post dominated is very important. That means C has to be present after N. And there is one more condition. There is a successor of C in the control flow graph that is going to be post dominated by N. If these three cases are satisfied by the node C, I can say that C completely controls the execution of node N. In other words, node N is control dependent on node C. This is about post dominators. Okay, see, I have taken up same example. Okay, by taking up these blocks. Okay. See here, execution of F, it is not inevitable at B. See, even if this executes or not, it will not impact the execution of B. But if I consider E, in order to execute F, E should be completed. The execution of E is impacting the execution of the block F, in other words. Okay, for the node F, the execution of FE, okay, the execution of F is inevitable at E, in other words. So F is control dependent on B. F is control dependent on B. The last point at which its execution was inevitable. Okay. As per the previous definition, they are explaining this particular point. Okay. If you see this point, okay, there must be a node C with the following property. That is, if I consider B, at least two successors are there. Okay, and if I consider over here, C has at least two successors in the control flow graph, and C is not post dominated by N, and there is a successor of C in the control flow graph that is post dominated by N. Here they are considering the execution of F over here. Execution of F is not inevitable at this point, but execution of F is inevitable at E. After E, F should execute. Okay, that's why indirectly F is controlled. F's execution is controlled by the execution of B. After B, E gets evaluated or C is executed. Either one of them gets executed based on the condition evaluation. So at this point, execution of F, you don't know whether it will be carried out or not. You don't know. Okay, but at this point, in order to execute this has to be completed. That's what they're telling you. So F is control dependent on B. B is in turn controlling the execution of F. Okay, that's how you can explain about post dominators. suppose dominators. Then we have something called data flow analysis. Okay, that is how we can compute the data flow information. Okay, so first and foremost, we have to calculate definition use space. Okay, and we can define definition use space in terms of paths in control flow graph. Okay, how can I associate D comma U pair, that is definition comma use pair? Okay, when I can say there is an association existing between the U pair. Again, there are two conditions. Please focus here. There is at least one control flow path from D and U. By this time, you have to know about what do you mean by D and what do you mean by U. D represents definition of a particular variable. U represents use of that variable. Okay. So when I can say that there exists association between DU pair, whenever at least one path is existing between the definition of a particular variable and the use of a particular variable, and one more condition with no intervening definition of V. That means you don't have any intermediate definition which is killing the definition, previous definition. You are not going to have. We have already seen definition clear path. What do you mean by definition clear path? Same only they are explaining with the help of control flow graphs. There has to exist at least one path from definition to use without any statement in between which is going to destroy the previous definition of specific variable. In that case, I can say there exists association between definition and use pair. Okay, means VD, it reaches U. VD reaches U. What is VD here? Definition of variable V that reaches use of the variable V. In other term, I can call it as VD becomes the reaching definition at U. VD becomes the reaching definition at U. Okay. If in other scenario, if there passes, okay, if the control flow path passes through another definition, intervening definition E of the same variable V, then VE kills VD at that point. VD is the previous definition for a variable V and V is the new definition for the variable D, same variable V. Okay, in that case, V kills the previous definition for the variable V at that point. Okay, then after that, we have something called the exponential paths. Okay, how many paths are present over here? If these all are nodes they have considered, and how many paths are existing in between these nodes? From A to B, there are two paths via which I can reach B from A. There are two paths. If you see here, from here also I can reach, from here also I can reach. There are two paths. From A to C, if I consider, how many? 4. From here to here, I have 2. From B to C, again 2 paths. That's why it is 4. Similarly, the source node is A and the destination node is changing. Okay, so the tracing of each path is not efficient if I follow this strategy. So I can do much better if I go for this data dependency graph, or if I consider data transmittal within the nodes of the graph. So the source node is A they have considered, and these all are destination nodes in CFG. Okay. After that, we have something called DF algorithm. In short, I can call it as definition data flow algorithm. Why we have to use DF algorithm? Okay. So basically an efficient algorithm for computing reaching definition. What do you mean by reaching definition? We have seen over here. If there is a path from definition to use, then a particular VD, I call it as a reaching definition at U. Okay. And we are making use of DF algorithm. What do you mean by DF algorithm? data flow algorithm to compute reaching definition. And it is basically based on the way reaching definition at one node, how they are related to reaching definition at adjacent node. Okay, you know about adjacency. Okay, uh, consecutive nodes or the nodes which is existing beside the other node, immediate beside to the node which is under study. Okay. Suppose if we are calculating the reaching definition of a node n and there is a edge p comma n from an immediate predecessor node p. Okay, that is the predecessor node p can assign a value to variable e, then definition vp, which is n. We say that definition vp is generated at point p. See, in other terms, it's not complex. Okay, you can just analyze the things. Okay, which is under study now? Which node is under study? I'm studying the node n, and I'm computing the reaching definitions with respect to node n. Okay, and if there is an edge from node p to n, okay, from immediate predecessor node p, predecessor node p. If I can assign a value to variable v at a predecessor node p, predecessor node p means what? Post predecessor, predecessor. That is, you already have studied this. Okay. Then the definition vp, it reaches n. We say that definition vp is generated at p. If at all, definition vp of a variable v reaches a predecessor node p and v is not redefined at that node, then definition is propagated from p to n. We'll just check it out how they are computing reaching definitions. Okay, definition use case and how they are controlling definition, how they are computing definition, reaching definition of a particular node. Okay, so the equations they have written over here, the same example throughout this particular unit, they have considered the Euclid's algorithm for computation of this reaching definition. Okay. See, calculating the reaching definition at E. This is E block they have taken. Okay, that is y is equal to 10. How can I compute reaching definition at E in terms of its immediate predecessor? What do you mean by predecessor? D is going to be the immediate predecessor for a node E. How can I compute reaching definition of node E in terms of D? That is, I have to use the data flow algorithm. Okay, that is, I am computing E now, the reaching definition with respect to E. So, write reach E. Okay, in order to reach E, I have to reach out D. I have to reach out D. Then what do you mean by reach out E then? Reach out E is going to be the reach E, whatever you are getting divided by, that is the killing of that YE. We'll just check it out. What do you mean by YA and YE? Okay, these two statements we will check it out. Okay, YA union YE, that is gen and kill. The point at which the value is getting generated and the point at which the value is being destroyed. Okay. Both of them should be taken into consideration. Okay. Tomorrow I'll just explain about this thing. Okay. Tomorrow if I have class. Otherwise, next class I will just tell you about reach out equations. And this will be asked. How can we compute reach out definitions using DF algorithm? Using DF algorithm, I'll be explaining about this point by taking the same example. Okay. Any doubts over here? Any doubts over here for anybody? See here, first and foremost, you have to know this, how these two have come. These two are arrived with the help of DF algorithm. Okay, if you see over here, the DF algorithm, how we can compute reaching definition. Suppose if I have a node N and there is a predecessor node P. Via node P, how can I reach node N? Okay, and these 2 points they have explained with the formula in the next slide over here. Reach E is going to be reach out D. And how can I compute reach out E? That is reach E such that YA, that is generation of the value Y, and generation of the value, kill of value YA. See YA, if you just traverse backwards, okay, is there any point where I have defined the value for Y? So at this point I have assigned the value. I am taking the value for Y. After that I am not at all changing. The only change in the value of Y is over here at the node E. That's what. Here it is getting generated. It is getting generated for the first time, and at node E, the value, previous value is being killed. Previous value is being killed. So this is how I can compute the reaching definitions of a particular node by making use of a predecessor node. I have to consider predecessor node in order to compute the reaching definition. Okay.